Thanks, everyone. I know I'm competing with sunshine and I'm between you and the party, but we'll make this as efficient as possible. I'm here. It's inevitable. Every conference in 2025 is required to talk about AI in at least some percentage of their sessions. And today I'm here to talk about the intersection of software architecture and AI. There's some pretty clear intersections between lots of roles like developer or building stories or search, but architecture and AI is tricky, so let's talk a little bit about this intersection between these two forces. And I'm going to do this in three parts. I'm going to talk about using GenAI as an architect. Is it possible just to fire all the architects and let GenAI do our architecting for us? We see what that looks like. We'll talk about the role of an architect as a coder. Are there ways that we can use generative AI as architects to help us in some of the coding chores that we need to do within our ecosystem? And then finally, probably the biggest thing we have to worry about as architects is not get enticed by the delicious complexity of the internals of the LLM, but how do you take the thing and put it into production? Because that's what we have to do as architects. We have to take things like analytics and machine learning and AI and put them into production. And turns out there are lots of different categories of things to help you do that. So let's talk about each of these in turn. And we'll talk first about GenAI as an architect. And this book, so a little bit of a parenthetical announcement here. You may have seen 2 copies of this book at the ThoughtWorks table out here, which are going to be raffled away. They're going to notify the winners by email, so you had to give your email address to join. And they are signed by 2 of the 3 authors, because myself and Mark are here, and we're 2 of the 3. They actually created bobbleheads of us here on the cover of the book to represent us as the authors. But this is our most recent book on software architecture. And one of the distinctions we make in this book about software architecture is one of the jobs of a software architect is structural design. Given some problem, you need to design an architecture for it. And that, in a broad sense, consists of 2 activities: analyzing architecture characteristics or the capabilities of the system, and then analyzing the problem domain or the behavior of the system. Now, one of the tropes that you commonly hear in the design world is that you should use emergent design as much as possible. And here's the idea of emergent design. If you think you're going to end up with a lorry, you shouldn't start by designing a lorry. Instead, what you should design is a roller skate, and then a unicycle, and then a bicycle, and then a motorcycle, and then a car, and then a lorry, learning more about things with wheels at every step along the way and letting the behavior emerge over time. And that's great for the domain or the design or the behavior of the system, because that's why you're building the piece of software, is to capture some behavior. And it's good to emerge and adjust as aggressively as possible for that. But you can't do that for architecture, because the capabilities of a roller skate have almost nothing in common with the capabilities of a lorry. A simple little website is nowhere near as scalable as something that has been built to support 200,000 concurrent users, because design is about behavior. And we want to emerge behavior over time, but architecture is about capabilities. And you can't emerge capabilities, they require planning. Rebecca Parsons at one point convinced me that there is no such thing as an emergent architecture. There is emergent design. There's evolutionary architecture. I'll actually touch on that in just a second. You can create capabilities and build ways to evolve those capabilities as the needs change, but you can't just let it grow like weeds. And that's a fundamental problem of trying to replace an architect with generative AI, is that when we ask generative AI to give us a solution to a problem, we're always asking about the problem domain and the behavior of the system, but When humans write code to solve problems, they also have to take into account the capability of the system and the trade-offs inherent with architecture characteristics. So because it can build nice algorithmic solutions to things is great, but it's missing a huge part of what a person has to think about and the considerations you have to make as an architect to make it actually scalable or actually secure or lots of other desirable characteristics that have nothing to do with the behavior. And I want to talk for a second why it's so bad at helping you with architecture decisions. And this comes down to the way that generative AI works underneath the covers. So as a developer, I need to ask GenAI a question. And I'm going to ask it something like, how do I configure Kubernetes? Well, there's a giant corpus of knowledge out in the universe about how to configure Kubernetes. And so this is a giant matching machine. So it's going to find lots of things that are very, very similar to the problem you have. And it's going to give you a pretty good answer back because statistically, lots of people have solved this problem. And hey, I can give you a good statistical answer for that. The same for other sorts of problems that have been solved millions of times. Help me with this regular expression. Lots of different, very close exact matches there. Because remember how these things work. They're vectors. And vectors contain both magnitude and an angle. And the angle is how close it is relations, and the distance is how close in relation they are to finding a match between something. And here we're finding matches really, really nicely, but when it comes to acting as an architect, well, first of all, the first two problems I gave it had an obvious, discrete context. As a developer, I need help configuring this thing. But for an architect, got to give it context for the problem I'm working on. So now I'm going to give it this giant pile of context. I'm building this system. It needs to do this. It needs to do that. It needs to do this. It needs to do that. And now, finally, what are the trade-offs? Hand this off to generative AI, and it's going to go out here and try to match something, but it could very well be that no one on earth has ever solved this particular problem before. This particular problem of technologies and constraints and good stuff and bad stuff and old stuff. And so the chances of it finding a good match are not great, but generative AI, of course, gives you its terrible answer with the exact same confidence that it gives you its great answer. Because it doesn't know if its answer is good or not. It's just a statistical pattern matching machine. And so very often in software architecture, you're not solving problems that have been solved hundreds or thousands of times before, where there's a giant corpus of knowledge. You're solving unique problems, maybe even completely unique problems, and that's really, really bad at solving those kinds of problems. But that not all hope is lost, because it turns out that LLMs are not great for trade-off analysis, but in fact, they're too good at trade-off analysis. And this is actually the secret to making good use of it as an architect. There's a famous quote by Pablo Picasso that computers are useless. They can only give you answers. Of course, the subtext being, I want something that can give me questions. Well, now we have that. Picasso would be so excited about ChatGPT because computers are completely deterministic. The entire financial world would collapse tomorrow if spreadsheets started hallucinating. That would be a bad thing for accountants everywhere if suddenly, don't know if that number's right or not, but of course LLMs are non-deterministic and they can hallucinate, but they're also really good at gap analysis and raising good questions for you. And that's where it's really useful as an architect. Don't trust its answers, trust its questions. Because it may find a hole in your design that you didn't think of, and it'll pitch something. Very often you ask it, give me 10 pieces of advice, and 8 of them will be ridiculous or throwaways, but 2 of them will be, oh, I didn't think of that. Maybe I should consider that as one of the risks or one of the considerations or one of the trade-offs. That's what it's really good for, is helping you generate questions for gap analysis and helping you untangle some things and maybe helping you find some question that you didn't consider before. So it's great as a question generator. That's the first really good use of generative AI as an architect. The second one One of the trendy things right now, within the last few weeks, in fact, are these agentic coding assistants. This is, in fact, as we were talking about in the panel we did today, one of the hot spots of innovation right now. So large language models, when they first came out, they could talk really well, but now we're starting to wire them into behavior much more, where the words actually become actions. And this is really evident in agentic coding AI assistants. So now we have tools like Cursor that can modify multiple files at a time, that can move things around your file system, they can generate shell scripts and manipulate things, etc. Those are getting really good, and that leads to agentic coding assistants and some semantics like a prompt to code, or CHOP, which is chat-oriented programming, or vibe coding. I just recently recorded a podcast about vibe coding, and there are a couple of things interesting about vibe coding. The main one probably being that semantic diffusion is when there's a term in the world and then the meaning starts drifting because everybody uses their own meaning for the term. And the AI has just accelerated that to a ridiculous degree. So where vibe coding came from, this guy wrote an entry on one of the social media networks and did a little blog entry about vibe coded the solution this weekend, and it was great. Vibe coding is just, having the AI generate code for you. Don't pay much attention to the output, just throw away stuff that doesn't work and just kind of stay in the flow state. He was talking about how great it was to not get bogged down in details and just stay in that creative flow that we all really crave as developers, how awesome that was. And that's basically the message of his blog entry. And then every pundit in the ecosystem picked that up and decided their own definition of vibe coding, which included things like fire all the developers, we'll just let the AI do all the coding for us. And then, of course, within a week, the vibe coded site, he came back online and said, hey, I'm having some real problems. It looks like there's a denial of service attack on my vibe coded site, and I don't understand any of this code that's there. So can somebody help me configure this? I think I've got a really serious security problem here. Yeah, you do. Welcome to vibe coding, which is the problem. But the more fundamental problem with vibe coding is that it's only going to deal with the behavior and the domain, all these important things that humans have to think about, like security, but also like scalability and elasticity and all those things that require balanced trade-offs. Vibe coding is really just always going to iterate on that behavior and domain, and it's really hard to get it to consider the balance that we always have to consider as architects. The third problem, you're all familiar with the ethics problem in the AI space, I'm sure, of the trolley car problem. Trolley car problem is there's a trolley car careening down a track, and it can either hit a group of people or it can hit a baby carriage and kill a baby, and you could either pull the switch and have it kill one group of people or the baby. Which one do you pull the switch to kill? This is a conundrum in the ethics space because, of course, you don't want to pull the switch and kill either one of them, but if AI is having to make decisions about things, that is the trolley problem. This is a fundamental problem in self-driving cars. If this comes up, how do you solve this problem? We can't write algorithms for it. The fundamental ethics problem in AI, that's not the problem I want to talk about. This is the common one you hear about. I want to talk about the paperclip problem. This was proposed by this guy in 2003, Bostrom, and it's a thought experiment about prioritization. So let's say that we get agentic AIs wired up really well, and we can have language translate into action, and we convince this AI that you need to become very efficient at creating paper clips. This is your number one priority, is creating paper clips. Eventually, that machinery will take all the resources on planet Earth, including all the iron in the humans, to create more paper clips, because that is its sole motivation, is creating more and more paper clips. That is the paperclip problem. This is a thought experiment about AI posed in 2003, but you know what? It always happens. Philip K. Dick got there first. He wrote a story exactly about that in 1955 because Philip K. Dick has predicted our dystopian future almost to an uncanny degree. The paperclip problem indicates the tendency toward generative AI to create very complex solutions. So when Gen AI does provide a solution from an architecture standpoint, it tends toward boil the ocean. And there's a reason it tends toward boil the ocean, because how many beautiful, elegant solutions to problems exist out on the internet versus thousands of solutions of giant companies trying to sell you overly complex solutions to problems? That is the solution space it is choosing from. It's not going to default to beautiful, elegant solutions. It's going to default to big, giant, complex solutions, because there are more of those represented in the internet than the simple ones. And so a lot of solutions tend to be very complex. We did a few experiments where we asked GenAI and tried to iterate on GenAI with a prompt for a problem we had already solved in architecture and had a good, elegant solution for. And it took many, many, many iterations for it to suggest something close to ours. And all the ones before it were very, very complex solutions. So be careful about advice. It may be very complex. Okay, let's talk about the architect as a coder. One of the things that Mark and I always advocate strongly for is that software architects need to be involved in coding in their projects and need to be hands-on, because the closer to the context you are of the solution, the more knowledgeable your decisions, the more knowledgeable your trade-off analysis can be. And there's a really distinct way you can be involved in coding on your projects, and that has to do with this concept of architectural fitness functions. This was an idea originally created by Dr. Rebecca Parsons, who was the one who explained to me in no uncertain terms that you can't have an emergent architecture. She was a university professor for a while. She worked in a company on genetic algorithms, which are algorithms that mutate themselves and produce new results. She eventually became a ThoughtWorks consultant, which is when I met her and she first described this concept of a fitness function to me. She eventually became the CTO of ThoughtWorks and the emeritus CTO at ThoughtWorks. But one of the things that she created, an idea that she borrowed from her time working on genetic algorithms, was this idea of a fitness function. So when you work on a genetic algorithm, you have an algorithm that has an initialization stage and then an evaluation, and then you have an ending condition. If it's not met, then it mutates. And there are lots of different ways you can mutate. That's a lot of the science of genetic algorithms, is how it does this mutation. But you occasionally, as the creator of one of these, want to guide that mutation. So if it's picking a random number and you notice that small numbers give you better results, you want to tell it pick smaller numbers. That guidance is called a fitness function. You're trying to get more and more fitness out of the genetic algorithm. Rebecca's insight into this was, let's apply this concept of fitness to a software architecture, because ultimately we want our software architecture to be as fit as possible, meaning it exhibits the desirable characteristics that we have defined for it. And so that led us to this definition in our Evolutionary Architectures book of an architectural fitness function. This is any mechanism that provides an objective integrity check on some architecture characteristic or combination of architecture characteristics. The any mechanism part means, so this is very similar to the concept of a unit test. But a unit test is really just there to test the structure, maybe the requirements of the system. It doesn't necessarily check the architecture characteristics. You can't use just unit tests to check all possible architecture characteristics, and so fitness functions are broader than unit tests. Software metrics are very often used for this. And in fact, if you already have a tool like SonarQube wired into your project, you're already using architecture fitness functions, because you're checking the internal structural quality of your code base to do that. There are unit testing libraries to do this. I'll show you a few of those in just a second. But some architecture characteristics we need monitors for to measure at runtime. Scalability, elasticity, availability. I have to check the runtime system to see if those are true. Things like chaos engineering are a perfect example of this concept of fitness function. This was the innovation that Netflix had, where they had agents that ran in their production system and caused things to fail, so that they had to code defensively against that, so that when things did fail, they had already coded around that problem. Their philosophy was, it's not a question of if your system is going to fail at some point, it's when. And now the follow-up question is, well, what are you going to do about it when that happens? That's this whole idea of chaos engineering. And as we've seen, since we defined this idea, lots and lots of tools have come out to do this, which I'll show you in a second. The second part of this is that fitness functions have to have an objective measure, because that's the way you test things, is have objective measures for them. Some architecture characteristics are kind of slippery, like maintainability. Well, there is no objective measure for maintainability, but you can decompose that into things that are measurable. So that's what we call a composite architecture characteristic, but that's part of the key, is getting an objective measure for it. And this may apply to a single architecture characteristic or combination of architecture characteristics. So let me give you a simple example of what I mean by an architectural fitness function. Let's say that you're an architect and you're working on a component-based system of some kind. Most of what we work on these days is component-based, and one of the things you want to try to avoid as an architect are cyclic dependencies between your components. That's where you have one component that talks to another component, which talks to a third component that depends back on the first component. This is bad because now I can't just reuse one of these components. If I want to reuse it, I have to take the whole rat's nest of these components with me. And if these components are tangled up with other components, before long, my whole code base is tangled up in these big cyclic dependencies. This is a great example of something that when I was a young developer, we used to call this bit rot, but Wikipedia seems to think it's called system rot. And this is the idea that any old piece of software has to be terrible inside because it's sort of rusted or eroded internally over time just because of its old age, which doesn't actually happen in the real world. Software doesn't actually rust. But this is what they're talking about in many cases, because if you have 3 of these in your code base, it's no big deal. If you have 100 of them in your code base is trash. And so there's some line where it becomes a big problem in your code base. But here's the problem. The universe is actively fighting you on this. Because as you're coding along in your favorite IDE and you reference some class you haven't used before, what does it do for you? Pops up a dialog, says, do you want me to auto-import that for you? You haven't read that dialog in years because you know exactly what to do when that pops up. You slap it away by saying yes, and you keep typing as fast as you can. Nobody reads that thing anymore because why would you bother reading it? You know what to do. Most of the time it's great. Every once in a while it's doing that. How do you prevent that from happening as an architect? Because I want to build a code base that I can build on for long periods of time. That's an architectural fitness function. This is a tool called ArcUnit that understands package structure in Java. You wire this into your continuous build, and now you no longer have cycles in your code base. As soon as a developer tries to add one by accident, it catches it, and you get fast feedback. And that's a term you're going to hear me use several times here, because the essence of agility in architecture is not the absence of architecture. You need architecture. The essence of agility in architecture is, can I build fast feedback to architecture changes? Agility is about fast feedback, and we need fast feedback on our architecture. This is fast feedback on a structural problem in my architecture, and this allows me to prevent that. There are lots of tools that allow you to do this. Here's a tool in the Java space, the most mature of these, which is ArcUnit. That's the example I just showed you. This also exists in the .NET space. Here is ArcUnit Net, and there's also NetArcTest, both of which in the .NET space. Here's the one in the Python ecosystem, PyArcTest, PyTest Arc, some combination of those things. And here's one in the TypeScript, JavaScript, ECMAScript ecosystem called TSArc. So there are tools in lots of these ecosystems that allow you to do this. So this is one of the responsibilities of a software architect, to build these architecture fitness functions for the important things in your ecosystem, to make sure the structure is correct, to make sure the constraints are being honored, and all sorts of things that you can govern in an automated way. Just like setting up a cyclic dependency test, I want fast feedback for things that may affect the structure of my architecture. But here's a problem that Mark and I have run into, is the reason you never see architecture books that have a lot of source code in them is because as soon as you pick a platform, you've limited your audience to a very narrow slice of the entire world. Because now only Java or only .NET or only Python people are going to be interested in your architecture book. And this is a big problem for a lot of architects who are in polyglot organizations. We have some Java solutions, we have some JavaScript, we have Golang, we have other things. I really want to write governance rules that are universal, but I have to write now a Java unit test and a NetArch test, unit test, and replicate some of those same things. So this is a preview of the next book that Mark and I are working on. This idea of architecture as code, and using the large language model, the second letter there being most important, language, it turns out that large language models are really, really good at translating pseudocode into actual code. And so, for example, let's say that we have some sort of structure like this, some sort of component structure that, of course, reifies into a directory structure here with ticketing, and these components all exist as directory structures in my ecosystem. This is the relationship between those things. And we design that as an architect, but then everybody starts coding this thing, and then after production, I go back and look, and it's like, wait a minute, where did mobile connection come from? That's not a component I designed. But of course, because components relate to directory structures, it turns out that there was one team that didn't like the code in the other part of the team, and so they decided, I'm going to create my own package and just put all my stuff there so I don't have to deal with all their code or the little thing. And it's like, but now there's a new component here that I didn't create. And if you actually look at the relationship and the dependencies between all these things that ended up in production, this is what it looks like. And this is like, this is not what I designed as an architect, but this is what we ended up with because there's no constraint. And I don't find out as soon as somebody creates this new component in my system. Of course, this is an example of misalignment between what we're trying to achieve as the architect and what actually gets created. This is this idea, we're creating a very, very, very lightweight architecture description language where you can describe suitable things that we want in our architecture. I want to define domains here. I want to define a system with ticketing as ticketing, customers, customer, and then assert that classes are only contained within subdomains within these domains. And I can generate now a unit test from the pseudocode that is concrete code. And I can generate this in Java or .NET or Python or whatever. Now, if I'm purely in a Java ecosystem, this is probably all I'll keep, because this is exactly what I need, and I'll modify this. But if I'm trying to create something that's cross-platform, I'll keep the architecture decision record almost as a more precise architecture decision record and use that as the definition for the desires I want within my architecture. This allows me a consistent language across a lot of different, in fact, 9 different intersections in architecture that we're talking about, a way to express those things in a consistent way. Another example, define domains and define components within that domain, and assert that code is exclusively contained within components. And here's the corresponding source code in ArcUnit. This is the fast feedback I was talking about, because unit tests in your application, when they break, it's a bad thing. Oh, a unit test is broken, we got to go fix that. But when one of these breaks, it's a placeholder for conversation. Because as an architect, if somebody adds a new component, I want to know about it. Maybe there's a good reason they're adding new component. What I don't want is somebody adding one and me only finding out about it 6 months later after we've gone to production. This is the fast feedback I'm talking about. As an architect, when I design a system, I want to know if changes have happened to it. Just like a building architect, if you're going to change a load-bearing wall, I want to find out as soon as possible before you build more stuff around what should be a load-bearing wall. It's exactly the same here. This is the mechanism how you can get fast feedback on the structure of your architecture when people have made changes, whether good changes or bad changes. That's up to you to decide, but you want to know exactly when it happens, and that's exactly what this allows you to capture. The other thing this allows you to capture is to build constraints within your system and to govern things, to make sure that people are applying what you need, what you're after, what your goals are in that architecture correctly. So, for example, a layered architecture, part of the reason you choose a layered architecture is you want to separate each layer by its technical capabilities: presentation, business, services, persistence. And I want all the persistence code to be there. And the bad thing in this architecture is if I allow persistence code here, because I no longer have a layered architecture, then I have sort of a ball of mud that's sort of in layer shaped, but not great. So I want to be able to control that kind of behavior in my architecture, including things like open and closed layers have to be respected. So when you design an architecture like this, a closed layer means only requests from the layer above can come in. But some layers are optional, so I'll let those be bypassed. And that's what I want to create a constraint for. I don't want anyone to bypass a closed layer, but it's okay to do so in an open layer. I can express this as an assertion, define these definitions of things, and then assert presentation has no dependency on services or persistent. In other words, it has no communication to those layers that it shouldn't have, and this is ArcUnit. This is a great example of the APIs built into these tools that understand. So this is using this family of matchers called the Hamcrest matchers that let you write these very English-like assertions and define these rules about layers and what responsibilities are and things like layers. Another example, I don't want anything except the persistence layer to be able to talk to the database. So now I can say what things should be able to talk to the database and then assert that no classes have the connectivity or the capabilities of talking to a database. This one ties it specifically to Java, but we've got an example of this. It just says no SQL capabilities, and it generates the correct code in .NET and Python for the correct classes that you would need in that platform or ecosystem to be able to connect to the database. That builds a constraint so that people can't do that connection for you. So this is a great assistance for architects, because one of the things we're always needing to do is build these governance rules, but it's kind of a lot of overhead to build it in multi-platforms and learn the APIs. This is a great shorthand way to be able to generate this code for you. One quick little bonus tip, and I don't know why more people are not talking about this. If you're going to use GenAI to generate code anyway, why don't you have it generate functional code instead of imperative code? Imperative code was created for humans to model object-oriented systems, and functional code is often, once you learn to read it, much cleaner. Let me give you an example of this. It's more declarative, it's immutable by default, it has a lot of desirable characteristics, and it's often simpler. So let me show you an example of this. Here's a bunch of mundane tasks: capitalize first and last name, remove everything except spaces, apostrophes, and dashes, sort them, and then remove duplicate entries. Tell generative AI to generate this, and here's the imperative code it creates for you. So here's a for loop to go through and clean the names. There's a whole bunch of stuff down here to handle. So this is smart enough to figure out that some names have apostrophes in them and hyphens, and you have to do the capitalization around those. So that's what all this stuff is. Nested for loops to do all that, of course, because this is all imperative code. And then some test code to do all that stuff. So now I'm going to change my prompt and tell it, there we go. These are all the for loops inside here, and of course this is Java, so there are 3 null checks, of course Java. Now add using functional programming to the prompt and change nothing else, And here's what it produces. Here's the fundamental algorithm. Names.stream, map to clean name, filtered to empty names, capitalized, distinct, sorted by last name, and then collect them into a list. And if you don't know functional programming, that's not bad. In terms of readability, it's very declarative as to basically what that algorithm does. Even the messy stuff with all the names, no loops. It does it all with streaming APIs in Java. This is not some exotic functional programming like Haskell. This is Java. Java supports all this functional programming stuff now. So this is just more stuff that's built into Java now, all the streaming, etc., and the ability to test all that stuff. So a lot simpler, a lot less of it. I can't resist. And no loops and just 2 null checks now. I can't resist showing you the same thing in Clojure, which is an exotic functional programming language. Here's the main algorithm in Clojure. I mean, there's almost no programming symbols in this. It's almost all just the things that describe the thing I'm doing, which is, of course, one of the goals of Clojure, which is a Lisp. So you can get really, really clean code in functional programming languages often. It is a little harder to read initially. You have to understand functional programming concepts like maps and filters and all that sort of stuff. But you end up with a lot less of it. And that's one of the goals, is not get drowned by a lot of generative AI code. But there's a big caveat that goes along with this, that the boil the ocean problem that we have generally, when it boils the ocean with functional programming code, it gets really ugly really fast. And so you have to be careful that it's not giving you some really crazy complicated functional programming code that nobody can understand, even experts. But that's true with imperative code as well. Okay, let's wrap up by talking about the real job that we have as architects around AI, which is productionalizing AI. I mentioned before this ThoughtWorks radar thing. This is something that we put together twice a year. And it's important to understand how this thing comes about. This is purely curated from projects. So we have over 200 software projects going on around the world. And to get on our radar, the way that happens is that one of our development teams has to nominate something and say, this is working really great for me, or we really hate this a lot, either of those 2 categories. And then regional people gather all those things up, and then we meet face-to-face twice a year. Our last meeting was in Bangkok, Thailand, and we curate all these things on our radar. We generally start with about 300 of these blips, and we filter it down to about 100 to make it fit. And the last few radars have been dominated by AI stuff, and that's what I want to talk about here. One of my colleagues, Brigitte Berkela, is our AI expert, and as we're going through this, she categorizes a bunch of these things, and I want to talk about the categories here and a few of the tools, because that's what's really important to us as architects, is how many different ways do I need to think about productionalizing AI and AI-related things. So, first, I need to discuss a little bit of terminology for our radar. Oh, by the way, our next radar we're going to put together in September of this year, and it's going to be done here in Bucharest. So all the people who put together the radar are coming from all over the world to meet here in our ThoughtWorks offices in Bucharest to put together the next edition of our radar in September. We had for AI about 80 proposals, and for things on our radar, things that we end up in assess means that those are in active research and development on our teams, which means that we're using it, it looks promising, but it hasn't proved itself yet. Something that's in trial means that we've used it a long time, and we've put it in production, and it's working as we expect in production, so that's one of the milestones to get into trial. Adopt means it's really, really good at what it does, and we really love it. And hold is, we hate this, and it's really not stop using instantly, but don't start anything new in it because we think we've got a better alternative than that. There are some things that get kicked out during the meeting, that's that category in gray there. And then finally, some things move from the last radar on to the new radar if they are still relevant. So with that key in mind, let's look at a few of the categories of tools that came up on volume 32 of our radar. And one big category, of course, is the one I was just talking about, which is AI-assisted software development. And you'll see a lot of blue cards there, which means these are all things that have moved into trial in our projects. We're actively using in production-based systems and finding good uses out of them. These are things like Continue and Cursor and Cline, which are all these agentic coding assistants that we've seen. There's prompt-driven development, which is in trial in minor cases. That's the vibe coding or CHOP-oriented programming. There's a whole category of things down here for things that are coding-related tasks, but beyond coding, including synthesized. This is a common problem we had forever, which is I need realistic production-like data for testing. What synthesize does is go through your production data and filter it and create realistic production-like data, only a small subset of it. Humans have to do this. Now AI, the filtering capabilities of AI, really good at getting representative data without, exposing things it shouldn't expose, et cetera. So synthesize is another tool called Tonic AI that didn't make our radar. It's in that same category of tools. Models, there's not a lot of innovation and things that we have to look at in those. We did look at all the DeepSeek stuff, and those are now all in evaluation. But models are all things that are kind of continuously in a sort of slow motion evaluation. Building LLM-backed applications, and in particular, RAG and information retrieval. This is a giant hotspot right now. And in fact, a kind of an interesting long-term trend we see is that at each edition of our radar, different little parts of the ecosystem are going to get these hotspots around it. In fact, one of our themes for our recent radar was the R in RAG, because there were all these tools and frameworks and libraries supporting the retrieval part of RAG. And we expect that different parts of the ecosystem will see these bursts of innovation as people figure out clever things, and then people build clever things on top of that, which is, of course, the way an ecosystem like this grows and evolves. Things like Fusion RAG, which combines data from many sources, not just the RAG database, but from external sources and also other databases, and tries to fuse all that together to make more coherent results out of it. Corrective RAG, which uses heuristics to fine-tune data, so you build rules in it, almost like guardrails, where you're building rules that will pre or post-process the data to correct things in it that you know are incorrect. So that's particularly true if you're trying to capture highly accurate results. One of the things that's always confusing is how did we reach this conclusion? And so there are more and more of these tools that let you see a little bit of the thought process, or the processing process that went on. Graph RAG gets user navigable graphs as to how it reached conclusions for things, so you can get some insight into the observability of LLMs. We use that in production. It's quite effective. Agents are also very popular, and we're seeing a rise in this because this is the kind of the next step of translating language into action, and that's exactly what's happening with these things. Building AI search, that's the only one of three of our AI in an adopt. But this is a really obvious use of AI. I've never seen a large organization whose documentation wasn't scattered in a half a dozen different random places. Some in a wiki somewhere, some in a Confluence, some in who knows where, in the Lotus Notes database somewhere. There are a bunch of these tools now that are taking all those disparate things and slurping them all up and making them navigable. And that's a fantastic use for AI, because somebody needs to go through all that. And the pattern matching in AI is a great way to do that. So there's a whole category of tools that allow you to do that kind of stuff around enterprise and work AI. These things are important to us. The categories are important to us because, as tempting as it is for us to try to crack inside the LLM, the thing that we really care about is the supporting ecosystem. Things like patterns for use of LLMs. Things like, well, can we use a cheaper LLM most of the time, but then spot check its results with a more expensive LLM? That's a common pattern that has emerged to keep the cost down for LLM. So we're seeing patterns and anti-patterns emerge here. I mentioned observability, things like evals and guardrails and coding assistants. And in fact, when you look at specific problems, one of the problems we have in our upcoming book is this medical monitoring system, Monitor Me, this microservice ecosystem where I have lots of different sensors, all of which may need the access for LLM capabilities, because part of the medical sensor is when people wake up in the morning, we want them to describe how they felt overnight. We're going to try to correlate what they talked about with their physical condition, so we need pattern matching in language to be able to do that. And so to be able to do that, we need a vector database and some RAG stuff, and we're going to need some context setting, and we're going to need guardrails to make sure that medical information doesn't leak out into an ecosystem where it shouldn't leak out. And we need evals to evaluate how well is this performing its task. This is sort of the measurement function for generative AI. We see a near-term future where this is going to become a really common sort of side capability for a lot of operational services. And there's already an architectural pattern that's quite common for this. If you look at the way a service mesh works in a microservices architecture, distributed architecture, each service has a sidecar component that connects to the service pane. And if I know every one of my microservices has that sidecar component in it, then I can build a service mesh and control monitoring and logging and observability all directly through that. So that's a way of building a cross-cutting capability on top of my existing ecosystem. Another example of that is data mesh. And in data mesh, we're trying to separate operational data and analytical data. So can we do the same trick we did with a service mesh, which is create an analytics sidecar and just use the same database for analytics? Turns out we can't do that, because analytics data is often in a different shape. Analytics are things like yearly sales and roll-ups and aggregations and graphs, things like that. Whereas operational data are things like catalog items and inventory and sales. And I don't want to have an impact on my operational data. And so the data mesh pattern says that you basically have two services that represent your domain, the operational service and the data product. The data product has all the analytical stuff in it. The code inside it does the transformations and other stuff from your operational data. And there's an asynchronous data pump that takes the operational data and pushes it into that analytical piece of your ecosystem. So that's your domain. And now this data product can communicate with the other parts of the analytics part of your architecture. And you can use that to either create outputs for things like direct reports or something like that, or to cooperate with another part of the ecosystem. The data in the data product could be the same as the operational data, but it could be several different databases because I need to store data in a different way. So now, if every one of my services looks like this, I can produce analytics report directly from my analytics part of my architecture, but it can also cooperate in a larger architecture. And basically what I have in a data mesh is two different architectures that are overlaid on top of one another. I have the analytics architecture, which is connected through the analytics services, and I have the operational architecture, and the only way they're joined together is the asynchronous data pump from the operational data to the analytical data. That's this idea of a data mesh. This is basically two different architectures overlaid on each other with a really well-defined connecting point, which is that data pump between operational and analytical data. We can see the exact same pattern applying in the AI space, because that's yet another cross-cutting concern in architecture. Analytical data, operational data, AI. And so this ecosystem we can easily see becoming a sort of a sidecar for operational services, talking to the shared LLM, but each with its own set of RAG set of rules, its own guardrails, its own evals, its own customizations that doesn't necessarily need to be global to the entire system. And this is what we're referring to, and a lot of people are referring to it as an agentic mesh. And so a data mesh has operational services and analytical services. What an agentic mesh says is that we also need the ability to have global resources like large language models, guardrails, evals, RAG databases, and state for our queries. And so that will fit into this overall idea of a mesh architecture. And of course, the analytics may need access to the LLM, and so does the operational data. But this now allows me to basically have three different parallel architectures: an operational architecture, an analytical architecture, and an AI-based architecture, all coupled together in very, very specific ways. This is the way I think we're going to apply a lot of this AI stuff to the distributed architectures like microservices we have, preserving the same kind of structure that we have in microservices, but being able to overlay these AI capabilities on top. That, I think, is where the architecture piece of AI is going, at least in the near term. So, to summarize what I've been talking about today, it's a great resource for solved problems. So any problem you have that's been solved hundreds or thousands of times, it's great to use this. It's a terrible resource for trusted solutions, but really good for gap analysis and for generating questions for you. In terms of architect as coder, LLMs make great fitness function code generators, which we use it for all the time. But watch out for maximum complexity rather than simplicity. And then finally, for productionalizing AI, the mundane but necessarily real-world impact on architects. But architecture patterns still apply. Things like mesh is going to apply to AI just like it did to analytical data. And so just because we're using this fancy new AI thing doesn't mean we're throwing everything we learned about distributed architectures out the window. So I'm now officially standing between you and the after party. So thank you very much for coming, and I hope you enjoyed it.